All right. So the first thing that we're going to write is a function that differentiates between elements of expressions, right? So taking an expression from the command line, we want to print from that on separate lines the type of each element, right? And what would be the elements? There can be integers, they can be operators, right, which would be plus, minus, multiplication, multiplication, division, and exponentiation, let's say, right, power. So we want to do that. argv. All right, so our string will be an argv0. Cool. So what I'm gonna want to do is we're gonna say something like while parser has next we're going to say printf parse of parse next. All right, so this is pretty much what we want. We're going to have something that we call a parser. So we're going to have a function called parser init that we call first, right? And all these functions, and we're going to pass in to the parser init argv0, all right? And we're going to have to write here three functions, right? Parser init, which is void of char star expression. That's what we want here. And then parser has next. I'm going to explain this in a minute. Which is not void. It's int. All right, and then parse next, which should return an object. So let's not say anything yet there. Parse next, no arguments. And I'm going to say that this guy returns a token. And I'm going to say it like this. And we're going to see what this means. All right, so and let's call this eval. Let's see, right? Because it's going to become an evaluator after a few iterations. So we want to work with an abstraction, which we call a parser. All right, and whenever we do that, whenever we design code, right, we have to design our abstractions, right? We have to operate with concepts that appear convenient for us to use. All right. Now, whenever I have such a concept, right, such an abstract object, most of the time the object cannot materialize from thin air, right? It has to have an initial state, and in most cases, whenever you have whenever you come up with this kind of concept, you're going to have to initialize it. Right? It's a very common thing, right? You would like to hide that under a carpet, and most often in mathematics, when you come up with these concepts, they come somehow materialize out of thin air. But when you implement them in computer science and in software, they have to initialize. So you say, oh, I'm going to have this concept, but it needs initialization. It needs some setup there so that everything is ready to receive the data, right? So we're going to initialize this parser with the string that we want to parse. All right, and then this string has many tokens, right? If we look at a token like the one that we just typed here, actually, right? Because we did type 1, or didn't we? I think I deleted it. Right. So if I have something like 1 plus 2 times 3, 4, 5, right? So this is the first token, which is an open bracket, right? Then we have an integer. Then we have an operator, which is plus. Then we have another integer. Then we have a closed bracket. Then we have another operator. Then we have another integer, which has more than one character, right? And all of these are the tokens, the basic elements that make up our expression, right? So we want to essentially separate these tokens and print them out, right? Now, whenever we have a token, right, what we want to do is have the type and the value. Each of these tokens has essentially type and a value, and we'll see how that matters to us. Now, having a concept, a token, right, that has more than one attribute. So I said type, value. Actually, we're going to see that we're going to want a precedence as well. We have to be able to encapsulate data together. And if you have some programming background, say in Python, you are familiar with the concept of an object, right? You have a class. The class is the prototype for an object, right? Inside an object, you can put multiple attributes, right? C is a lot less refined than this, less sophisticated. The thing that you can use is a structure for aggregation. You can put multiple things inside a structure. So we're going to create such a structure, and we're going to create a blueprint out of the structure. So I'm going to say struct, and inside here I'm going to have int. I'm going to have char star value. The value is going to be all right, let's make things easy for us. Char cval. So this will be a character value. We're going to see when all of them are useful. There's a int, which is the I value, right? Which is what we're going to use for integers. There's another int. We're going to just leave it an int, which we call the token type, and int precedence, right? And we're going to give a name to the structure, which we say token, and then here comes the really interesting part. I'm going to use this as a type. I write type def there, and this becomes a type, right? So if I don't have the type def here, this would be a variable like any other variable, but putting the type def here makes this definition into a type. So we can use this as a shortcut, right? I can use it here as a shortcut for the return type of parse next. All right? Now, if I don't use token, I can take this entire string, I can take this entire construct, and I could put it here. Oh, sorry. Right? So this will also be correct without the type, but much less elegant, right? So just to understand that this is just a shortcut. Type def. Okay, let's add the prototypes. Here. So at the point when we have established these three functions, we essentially have established a protocol of working with the concept, right? So we initialize it. We call parser init. Once it is initialized, right, we want to pick one at a time all the tokens from the string, right? But we want to know whether there's a token to pick. So we have this function that tells us whether there is one more token left in the input string, right? And if there is one, so this will return true or false, 0 or 1. So if there is one, we can go ahead and retrieve that token. All right. If this guy returns false, we don't know. We don't want to say what happens if we call parse next, right? So our protocol says that it's not okay to call parse next if parser has next returns false, right? Your entire system might crash. We don't want to be forced to say anything. All right, so this is the protocol we're establishing. If you're calling parse next when this is false, it's your own responsibility. So this is what we would like the program to look like. And what we're doing now is top-down approach, a top-down approach, right? So I have established the protocol before having written the functions, right? This is always a good approach. This is you should always consider looking at things top-down, right? There are two approaches, top-down and bottom-up, right? Both can be useful in various cases. At least, if you don't start top-down, at least at the end you should look at your design from a top-down manner. Why? Because whoever is a client of your library, right? So this becomes now a library. It's three functions which you could potentially put into a separate API, right? The client of your library only sees this. They're not interested in how this is implemented, right? So you want to understand whether things are clear enough and easy enough to use. All right? So either start top down, or at the end of your entire design, once you have sort of discovered everything you need to put in there, take a look at it and from a top-down perspective, say, well, if my client wants to use this library, how would he use it? Is it elegant enough? Is it easy enough? Is it easy to understand? And so on. All right, now I'm complicating things a bit, but what I'm going to do is essentially use a global variable to store the string. Nothing more than that. All right. We can take a lot of approaches here, and let's actually discuss all of them. But one would be to take, say, char to a string to parse. Right, and this should be, and because this is a global variable, it's outside of a function, it will necessarily be null, initialized with null, right? We want to use malloc to allocate some value, to allocate some memory there and use it, right? Now, parser init should at least take the expression and copy it into here, right? But we can actually do more than that. We can actually go ahead and parse the entire string ourselves and store all the results into an array, right? And then these two become just traversals, just functions that help us to traverse the array, right? So that will be one of the approaches. The other approach would be to actually have this guy parse one token at a time and return it, right? And sort of advance this string to the place in the string that has not yet been processed. Do you understand the difference between these two? I could do all the work from the very beginning, or I could do one piece of work at a time, right? The interesting thing about either of these two approaches is that it doesn't matter for the client. The client will not see a difference. This code at the top of the program does not change. So once we have established a protocol, we have the freedom of choosing our implementation, right? We have a variety of things, of methods with a variety of trade-offs that we have to consider, right? And that's exactly how things should be, right? So you should come up with a protocol with an API that allows you that freedom of implementing things in multiple ways, right? But it presents a strong enough abstraction to the client so that they don't need to know how it is implemented. All right, so let's take the approach where we're actually doing one piece of work at a time, right? So what we're going to do here is string to parse is malloc is char star. str string length expression, and I am writing things very quickly, right? So first of all, I'm going to allocate memory. This function gives me the length of an expression of a string, which is terminated by \0. We have to allocate the length of the string does not include the \0, right? So a string containing only \0, which actually has one character, has a length of 0. That is the empty string. So we have to allocate space for the \0 as well. We always put the +1 here. And then we would use string copy. Right, so we are going from, we want the destination, which is string to parse, and we want the source, which is expression. Okay, so this is what the parser init is doing. Essentially, copy the string there. Why do I want to do it here, and why don't I just do it in the main? Well, I'm going to take this string and I'm going to keep advancing it. Right, I consume a token. This is essentially a pointer into my string and can just be advanced forward, right, to the next token. Whereas this is not as easy to do with argv0, right? Changing argv0, which is an argument from the operating system, it's possible, but it would not be a kosher thing to do, right? We should avoid doing that. Is this clear? What we have done, essentially, we've taken this expression and we've copied it into here. Okay. Now, can we check that this is correct? We should always do, right? So we should write a little bit of a test. So I'm going to comment out this. Right, and I'm going to printf percent %s and string to parse. Okay, so now there's one more problem, right? This guy has not been declared yet at this point. Right? So just for the sake of this test, because it won't change anything else but the visibility, I want to move it here. All right, one thing that I want to verify, make sure of, is that I'm remembering the functions correctly. All right, so 35. Yes, no problem. It's warnings, and we're not calling those functions, so they don't represent a problem. Eval, and well, actually, we can say 1 plus 2 plus 3 times 5 minus 2. Okay, so probably in quotes. This should be argv1. So we have discovered a bug. Okay, so this tells us that the program is correct, right? We have allocated enough space and we have copied the file correctly, right? Everybody's following so far? Yes? Anybody's troubled by the pointers? No? Cool. So back to, actually we don't want to go back. I'm going to delete this. I'm going to move this back. Why do I want to move this back? I want to make another point. Why don't I leave it there? And the point is that the main should not see this. This is hidden from main. At the point when we take this into a library, this is completely hidden from main, right? It's an abstraction. It's something that is abstracted away. And again, this is an important thing to do when we design software. We have to be very careful about what we expose to the outer world. Why is that? Because as soon as we expose it, people start using it, taking advantage that is exposed, and then you have to maintain the backward compatibility. You can't change it as you please anymore, right? You change it and somebody's code breaks. If you don't expose it, if you hide it, then you can change it as you please. And that's also very important because it allows your design to evolve. It is very often the case that the first version that you put out, that you publish, is a proof of concept that just proves that something is possible. Then you go and start and add new features and you optimize it and you make it faster and use less memory and so on. And in the process, certain things that you have hidden, you want the freedom to change those things, right? And the fact that you have hidden them allows you to do that. If you expose them, people start taking advantage of that, and then suddenly you change them, somebody else's code breaks. What they expected to be there isn't there anymore. All right, so parser has next. So for the parser, what are we going to do? One thing we want to do is to allow spaces, but in between our tokens, right? But for the time being, let's not worry about that, right? So parser has next when the current the first character in our string to parse is not \0, right? So that will make it very simple. Return string to parse, star string to parse, not equal \0, right? So that's very easy to. This only works under the assumption that there's no white space in the string. So now let's look at parse next. What do we need to do? So we have several types of characters. All right? And we have to emit a token. And then when we call parse next, we are guaranteed to have a token. All right? So we might as well create one and allocate one. So token start result equals token star malloc size of token. So we allocate space for a token that we want to fill, and we're going to return not the token itself, because the token has variable, I mean, in principle it can have variable length because the program evolves, right? And we're returning a pointer to it. So we're allocating a token in the heap, right? We're filling it in with the relevant data, and we're going to return that pointer. Another important principle that I should have told you about when I introduced pointers is that C manipulates only stuff that fits into a register, right? And obviously the size of the register varied over time. Nowadays, the most common size of register is 64 bits. So it manipulates only entities that fit into 64 bits, right? So whatever you declare as variables, right, this thing, this thing, this thing, is a 64-bit entity, right? This guy is something that has a larger size. It can be placed in memory. It can be laid out in memory, right? But once it is laid out in memory, you can only refer to it via a pointer, which is a 64-bit entity. You can't take the structure as a whole, right? Let's see what would be the size here, right? So we have 1 byte for the character, and we have 4 bytes for each integer, so that's 12 bytes. So we have about 13 bytes for the structure, right? That's much more than 64 bits. And also, as the program evolves, we might actually add a variety of things in there, right? It doesn't necessarily stay that way. For instance, if we want to report errors, we want to take the column number, and maybe the expression goes on several lines. So we want the line and the column of where the token starts and ends, right? So it's quite possible that we might want to add things like this in the future. Not in the duration of this class, but assuming that this is a large project, you may want to do that, right? So obviously, when you manipulate things to entities whose size might change as the program evolves, what you want to manipulate really is a pointer to that. So remember, this is the basic principle. So we're going to return a pointer to the token and not the token because of that. So now we have to fill the token. Now, this is a pointer to a token, and there's fields in it, right? So we have to access the fields. And the operator to do that is token arrow, right? So we have token arrow, result arrow. And you see that the IDE already knows what I'm looking for, right? So I'm going to fill these fields based on what the string looks like. So we're going to start with trying to discriminate between all the 1-character entities, right? Which are operators and brackets, right? And to do that, I'm going to use the switch statement, which again we haven't seen before, but you hope Python doesn't have one, I think. So let's see how the switch statement works. So star string to parse. So this is the first character in the string to parse, right? And we're going to perform a discrimination, right? So we have case, and we have open bracket, and I'm going to write a break here. I'm gonna fill in with some code here, but let's do that once I have established this this pattern. And I'm going to do a bit of copy and paste. So there's going to be one for close bracket, plus, minus, star, division, and power. All right. So close bracket. All right. Plus, minus, star, division, and power. I wonder why. Okay, errors are gone. All right. So if we have an open bracket, let's define types for our tokens, right? So we have 3 types. We have integer, we have operator, and we have separator. let's call it. So the brackets would be separated, or scope, if you want. So we're going to say define int type, and we're going to give them integer values. It doesn't matter what values we have as long as they're different, because we're never going to see these values again. Parenthesis type, let's just call it like that. So 1, and define operator type 2, right? So these are the types. Now, for brackets, we have open and closed, right? So I'm going to have define var open to be 0, to be 1, and then all right, and then we need precedence for we need precedence for actually, I don't think we need these. Let's not over-engineer things. But we need precedence for operators, right? And we're going to consider that plus and minus have precedence 0, star and division have precedence 1, and the next one, exponentiation, has a precedence 2. And here we can't actually do definition because we actually want those numbers to compare with each other, right? So we're just going to use them directly. If we have a bracket, right, we're going to have that our result arrow token type equals type part type, right? Part type. I'm not getting them anymore. Oh, because I haven't added the semicolon. Semicolon. I don't have a precedence. I don't have an integer value. So the C value is going to be just the character itself. Okay, let's do it that way. So what happens in this switch statement, right? It's a discrimination statement. So depending on the value here, this value here can have one of these, this expression here, right? Let's call this an expression. This expression here can have any of these values, right? Can be an open bracket, closed bracket, plus, minus, and so on, right? So if it's an open bracket, right, we perform the actions here. We end the case in a switch with a break, which will take us outside of the switch. All right? If we don't put the break, which in C is legal, as it is in Java, there are languages where it's not. But if you omit the break, then from here you go into the next case. You just execute the code for the next case. And again, back in the day, people would invent all sorts of situations where this would be useful, right? And then that again would be the trigger for a lot of bugs. And then good programming practice nowadays says don't do that, right? So we're going to put a break religiously after every case. So here we just do the same thing with just that the value is this. All right. So this will be op type, and the result is going to be plus. And here we also have a precedence, right? And this is precedence 0. Because when we evaluate, remember, so 2 plus 3 times 4, 3 times 4 has to be performed first. And the addition has to be performed only after that. So we keep doing this. This is minus. All right. This is star and would have a precedence of 1. Sorry, star. And would have a precedence of 1. So actually for all these, it will probably be a lot easier if I just say here string to parse. Right? Because only when it's an integer, I'm going to not have a character value and rather have a integer value. So this would still be 1, right? And then if we do it this way, actually we can save on coding. We can stack 2 cases together. So you can say that for both plus and minus, we execute this. And then for both star and division, we execute this. And then finally, for this guy, we're going to have a precedence of 2. Now, what if the character that is at the top doesn't fit into any of these cases? All right, that's a valid question. And for that, we have a special case which we call default. All right. So on the default case, there are 2 possibilities here. Either we have an error or we have an integer, right? If we have an integer, the trouble is that we have to keep consuming digits until we exhaust them, right? So let's assume that for the time being there's no error. We're going to deal with errors later, and we're going to say while string to parse, right? Star string to parse, and then I'm going to employ a new function, is digit. So this is a function that comes from string.h. All right, and we're going to do result dot I value equals 0, and while is digit string to parse is, we have a digit. What do we do? And actually, I don't think I need brackets. Plus is this okay? Val, I val, right? Everybody understands this? So look what happens, right? And then we should do string to parse plus plus, right? And we said previously that we will always do it as a separate statement, string to parse plus plus. And perhaps this would be nicer to write as a for loop. Right, so we should say for, and then we don't have initialization. We have a condition, and then we can say string to parse plus plus here. All right, and then we don't need the curly braces. So it looks a little bit more streamlined. So here we're definitely expecting an integer, right? And we're assuming for the time being that there are no errors. So we're going to say that the token type is equal to int type, right? And then outside of the switch, we're going to return a result, right? Is this clear? All right. So we have our while loop. At this point, our program should be able to run. So gcc minus o eval.c printf parse next. And parse next, of course, is yeah. So let's put formatting string here. All right. So we want to actually let's add another another element to our protocol. Let's add something that prints once it has a token, it converts that token into a string, right? Because it's different how we convert a token from string to from whatever it is to a string. Depends on whether it's an integer or an operator. All right. So let's call it token to string, and we want to return a char star. Let's actually print it. So instead of saying printf here, let's say print token parse next. And this is something we also need to write. So it's going to be a function that returns void. I'm going to say void print token char star. And just to be all right, so we're going to have void print token char star, not char star, token star. What am I talking about? Token star t. So we're going to say switch again of token t, sorry, t type, right? Token type. And our cases are going to be int type, so printf and we're going to say of type int %d, and we're going to have here token ival break case opr type, and we're going to say now printf and of type operator with precedence %d, and then we're going to say what a token is, and that's %c \n. Let's put \n everywhere. Does it make sense? And then we're going to say t. What do we print here? We print the precedence and the c value break case. What's left? Parentheses, right? Type r %c, and then we would have t c1 and break. Now, normally we should have a default, right? If we don't provide one, the code will just exit, right? So if we don't provide one, what the compiler generates is this, and in this case, that's fine for us, right? Do nothing in case of not hitting any of those, right? And that's fine for us. So now we have the print token here instead of the printf, right? Which differentiates and prints and tells us that we're doing the right thing. Okay. So go back to this, and then let's do the eval, and there we go. Control C. We're stuck on the plus, and we're stuck on the plus because we haven't done a plus plus. All right. So what happens is that on all these cases, on this case, we're doing the string to parse plus plus automatically, right? So we're always going to end up after the last digit. But in the rest of the cases, we forgot to do the plus plus. All right. Okay, so this is our tokenization. And we forgot to put \n a few places. Here, for instance. And now it works all right, right? So if you look there, we have managed to tokenize, right? And one important thing is that we can deal with larger numbers, right? So you see this number being correctly extracted here. Okay. And we can also raise the powers. All right, so everything is correctly categorized. This is the first phase when you do any kind of parsing. This is called tokenization or lexing. All right. Now, all the elements in the expression, they all occupy one element in an array, right? I can actually have an array of tokens, right? Instead of having a string of variable-sized elements, I have an array of tokens, right? And each token is well categorized, right? Pretty much each token has the same size, but actually we're being amateurish in allowing it to have the same size, because you could save some memory by using exactly as much memory as it needs. In each token, some of the fields are not used, right? If the token is an integer, we're not using the precedence, and we're not using the character value. If it's an operator, we're not using the int value. If it's a parenthesis, we're not using the precedence and the int value, right? So it would be good if we could actually compress. But never mind that. We can discuss how that can be done. What I would like to do is move on to the next phase, all right, in the evaluation. And talk about the Polish form for an expression. All right, have you heard of it? The reverse Polish form, actually. Have you heard of it? Some of you have. Okay, very good. It's called the Polish form because it was invented by a Polish mathematician whose name I can't remember, but you can Wikipedia. You can wiki it. It's a form of writing expressions without brackets. All right. So when we evaluate the Polish expression, we don't need. I mean, it has a rule for evaluation, and we don't need brackets in writing it. If I take the expression that we have just written here, I'm going to show you what a Polish expression is. And in order to derive it, we need the use of a stack. And we kind of talked about stacks before, right? We looked at the towers of Hanoi, and we explained recursion, and that was with the use of a stack. It's a collection of objects where you have a last in, first out discipline, right? Whichever object goes in last, that's the one that is going to come out first. If you want a real world analogy, in some kitchens there's this device to hold plates, right? Which there's a hole, there's a platter that on top of a string, and the string can be compressed, right? And as you keep adding plates on top of each other, so the first one goes on the platter, and all the subsequent plates go on top of each other. The weight of the plates press the string, right? And all the plates go down. So pretty much the plates are always there's just one. If the spring is calibrated correctly, there's always one plate just above the surface top, right? So you put them in, and then when you're going to take them out, you're going to take them out in a last in, first out discipline. You can think about that. And you might think, what's the big deal? Well, it's an extremely useful discipline and data structure in computer science. All right. So here's how this is going to work. Whenever we encounter an operand, an integer, we write it to the output. It's a very simple rule, right? So we see the 1, we're going to write 1 to the output. Whenever we see an operator, we put it in a stack. So I'm going to put the stack here. We have plus in the stack. Not always. There's a discipline there. But for the time being, the stack is empty. So we have nothing. The next one is 2. So I'm just going to write a 2 here. Let's put them separated by a space. So now, when I have a new plus, right, we have to look at the stack. We have to worry about the stack. So this plus that is highlighted, right, which is the latest plus, has the same precedence as the plus in the stack. Whenever the precedence of the current character is the same as the precedence of the operator at top of the stack, we extract one operator, we write it to the output, and only then we take this operator and put it into the stack. right? So the result is it's still this. I mean, you're looking like at it as it looks like the same plus, but it's not, right? So it's like I've extracted this plus. Oops, I've extracted this plus, right? And I've pushed this one. So it would be more interesting. Let's assume that this is a minus, right? Because then it's more interesting, right? So I extract the plus, which has the same precedence as the minus, and then I push the minus. So it's never the case that at the same precedence or lower goes on top of on top of the stack. Always, when I push on top of the stack is an operator with strictly higher precedence, right? So plus is out. Then this guy is the next one. So we're going to just write it out. 3876, right? Then we have a star. So you see the star is strictly higher precedence than the minus. So we don't extract the minus, we add the star, right? And then we're encountering a bracket. The bracket has the highest precedence. We consider it an operator, but has the highest precedence. So it always goes into the stack. 5 goes here, okay? And then I have a minus. So strangely enough, actually, the bracket behaves a bit strangely. It has high precedence when we put it in, has the lowest precedence when it's in the stack. All right, so it behaves a bit differently. So once it's in the stack, it has the lowest precedence. So I'm going to take this minus and put it on top of it. Okay, the next we have a 2. All right, now I'm encountering the closed bracket. Closed bracket has a very interesting effect. I take out everything from the stack until I encounter the corresponding open bracket. And I put it in the output. So I'm going to extract the minus. And then I'm going to see the bracket. And then all these disappear. And now the end of the expression here, we're just going to assume that there's a character saying end expression. It's sort of backslash 0, right? But there's no backslash 0 there because all of them are token now. I'm going to extract everything and put it in reverse order. So this would be the Polish expression. So how do we evaluate this? And show that we're essentially obtaining the correct value, right? So we're going to, in evaluating this, we're going to have now a stack for operands, for integers, right? So it's going to be a separate part, a separate algorithm with where integers are sitting into a stack, right? So when I see an integer, I'm going to put it in the stack. When I see an operator, I'm going to perform the operation between the numbers, 2 numbers at the top of the stack, and push the result back, right? So I see 1, I'm just going to put 1 in. I see 2, I'm going to see 2 in. I see plus, I pull 2 numbers, I perform the operation, I push back the result. I see 3876, I put it in. I see 5, I put it in. I see 2, I put it in. I see minus. I extract 5 and 2. The result is 3, and I push back 3. Right? Now I see star. I pop 2 numbers, right? And I put back the result. I'm going to just assume that it's 12,000-ish, right? So this is the result of star. And then I have the minus, right, which is I'm just going to pull 2 numbers and I'm going to perform the operation and push back the result, right? So this is going to be minus minus I don't know, 11,000 and something, right? And at the end, I'm supposed to have a single number in my integer stack, and that's the result, right? So is this clear how it works? So we're going to try to implement these 2 phases, taking advantage of the tokens that we've created, and essentially evaluate the expression. Okay. We won't have time to do it today, though. All right. So since we're talking about theoretical concepts, and I have 10 minutes, let me use those 10 minutes to introduce yet another concept. That concept is creating the tree of an expression. All right, and let me see if I can go to last year's code. Oh, one thing that we could do actually right now is to decide whether an expression is valid. All right. So when is an expression valid? Instead of I wanted to show you the tree. I'm not completely sure which one of these is, so I'll have to. I wonder if eval is. Not sure what this is doing. +2. Okay. So I can also show you some trees. Okay, this doesn't evaluate. This does. So for instance, for this expression, this is the tree corresponding to that expression, right? It's a relatively simple concept, right? We're going to want to build these trees as well. So since we don't have a lot of time, maybe I just introduce these concepts. All right, this program that was written back then was also checking whether an expression is correct. But what we did in the end was to just take a bunch of expressions, because it was very many of them, right? And run them as tests. So this is what eval is doing. It's not taking any expression from the command line, but it's invoking the evaluator with a bunch of expressions, and we want to see that the output is correct, right? So for instance, this one would be an incorrect expression, and it's correctly detected as incorrect by the program, right? The more interesting thing is, building these trees, right? So we're going to try to also learn how to do those drawings. All right, but is the concept of a evaluation tree clear? Yes. Okay. So yeah, 9 minutes. Definitely, we don't have enough time to do the syntax check. So I think I want to do that next time. All right. It is a natural byproduct. I mean, there's many ways of doing it. Let's talk a little bit about it. There's many ways of doing it, right? How would you do it? Yeah, but so in the process of doing that, how do you know when the expression is not correct, is not syntactically correct? So let's look at all the possibilities, right? One is, forget about Polish notation and everything. We have the tokens, right? At the point we have the tokens, there's a certain kind of sequencing that we're expecting, right? So what's the first character that we see? Either an integer or a bracket, right? Or an open bracket. This is the only thing that we accept, right? So essentially, once we see an open bracket, we can recursively expect an expression inside up until the corresponding closed bracket, right? Otherwise, right, we're expecting whatever is within brackets has the value of an operand, right? And we're expecting operand, operator, operand, operator, operand, operator, right? So we start with that, right? Assuming there's no brackets, we write a function that just traverses the string and checks that this alternation is there, right? And then once we have done that, which is very simple to do, we take the case of brackets, and we're saying, oh, I see brackets. Then recursively check that whatever is within brackets is a valid expression, right? And that would have nothing to do with, you know, trees or reverse Polish notation or right? Now, if in the process of translating from, we can do it in the process of translating from regular expression to reverse Polish notation, right? What would be the cases? What would you encounter? So actually, let's just assume that you use the algorithm as was given, right? So you convert into Polish notation, you get whatever you get, and you try to evaluate that, right? You will see odd cases necessarily, right? You might see that you don't have two operands for your operation, right? You might see that you end up with more than one operand in the stack, so the expression has finished, but you have more than one operand, right? Or you might see that you're encountering a closed bracket, right? And then you're emptying the stack and you haven't found the corresponding open bracket, right? All these cases will indicate syntax errors in the original expression, right? So that's all we have to do. So if we encounter these cases, then we automatically have also performed a syntax check. The only situation where you're going to get the correct result, meaning the algorithm ends with a single number in the operand stack, is when the expression is correct. There's no other way, right? So if you look at all the error cases that may encounter, then that's what will give you error case. Yes. Oh, but that will be not be a syntax error. Yes, it is an error, but that is not a syntax error. Okay, and the third one, which is also very interesting, would be using a grammar, which is actually something I managed to do last year. So let's see how we have time this year. And I have 4 minutes. Let me give you the concept of a grammar, not the code, right? So grammar, start symbol. Saying that, and we wanted to treat the precedence here. So we use this symbol, which is was introduced by it's called the Bacchus-Nauer notation. Not sure if you know who Bacchus and Nauer were. So Bacchus was the guy who invented Fortran, and Nauer was the guy who was, you know, his collaborator, and then became instrumental in developing Algol and Pascal. So from a start symbol, we can have so this is an expression actually. I'm going to denote it by E. An expression is either a digit, a number, and when I say number, it's a token. It's a token of type int type, or an expression plus an expression, or an expression minus an expression, right? And there's all the operators here, or open bracket expression. So this is what a grammar is, defines very clearly the expression, all right? Any string satisfying this, any string of tokens, right? Any sequence of tokens, because all of these are tokens. This is a token, right? This is a token, this is a token, this is a token, this is a token. And E is a grammar symbol. right? And we're saying that this is how we generate all the numbers. I start with E, and by applying these rules systematically, I can potentially generate all the possible expressions, right? Even though I cannot generate all of them because it's an infinite set, since I haven't specified the length, but I can enumerate. And if I have a finite set, I said, give me all the expressions of size at most 100, I would be able to enumerate all of them, right, and generate all of them based on these expressions, right? So it tells very clearly what an expression is. And then there's a very simple technique, right, to write a bunch of recursive functions that go from this to a recognizer, to a syntax checker. So hopefully we might be able to do that next time. So keep this concept in mind, that of a grammar. Obviously, I'm just scratching the surface here. But all right, so for the time being, we've learned how to tokenize a string, which is an important thing, right? And we're going to go towards generating, evaluating expressions, right? And generating the trees of one expression. Questions? Cool? Easy, huh? Good. Thanks for